that. Thank you for that. Let's begin. Thank you for pointing out that I had not noticed. Now, so we are looking at the Eisenstein's criterion. We had looked at rational root test last Tuesday, and we used this rational root test to factorize polynomials. But the Eisenstein's criterion that we're going to look at today, is only assisting us to tell if a polynomial can be factorized or not, but it cannot factorize that polynomial. So it does not factorize the polynomial. So if you are to factorize the polynomial, then you have to go back to what we did on Tuesday using the rational root tests. So the Eisenstein's criterion, we'll be using it just to tell that this polynomial can be factorized, this polynomial is reducible or is irreducible. And that is what I've stated here. That's what I've stated. I've said here that it's a simple approach that it shows that a polynomial is irreducible without factoring this polynomial. Now, so then I was now explaining how do you use this criterion to tell that a polynomial can be factorized or not. And so I was considering this polynomial, and then I'm looking at the coefficients of this coefficient, the leading coefficient, of this next coefficient, then all the way up to this coefficient that is multiplied by x, then I have the constant term. So for you to tell if this polynomial can be reduced, you think of a prime number. You think of a prime number. If it can be obtained, if that prime number can be obtained, of course, if it cannot be obtained, and then we also will conclude. But if it can be obtained, then this prime number should be able to divide this constant term, divide this coefficient, divide all these coefficients, but it should not be able to divide the leading coefficient. So you think of a prime number with those that can perform that. If it exists, you think of a prime number that can divide this constant term. That same prime number should be able to divide this coefficient, should be able to divide this coefficient, but it should not be able to divide the leading coefficient. So if that prime number exists, there remains one thing again to check. Its square, the square of that prime number should not be able to divide the constant term. Its square should not be able to divide this constant term. Now, if that prime number exists, then there's a likelihood that this polynomial can be factorized. If the prime number with all those properties that we mentioned exists, then the polynomial can be factorized. Of course, you now have to pick on another prime number if it exists, and again try the same. Now, those are the properties I've just put here. Those are the three properties. One, I said, check if you can get a prime number P that it divides all this and cannot divide, should not be able to divide the leading term, should not be able to divide that. And the square of that prime number should not be able to divide the constant term. Now, so let's look at an example just to then make it clear. Got an example. Now, we had done this example earlier on Tuesday, but we want to revisit it. I'm given this polynomial, and I want to check whether it can be factorized or not. So as we already have agreed that the step is, we think of, is there a prime number which can divide this constant term and divide this, but fail to divide one? Is there this prime number? that can divide this, and fail to divide the leading coefficient. And that prime number should also not be, its square should not be able to divide the constant term. So the prime number I'm thinking of is 3. Let me think of prime number 3. For instance, prime number 3 can divide 6, can also divide -3, but it cannot divide 1. Is that okay? So it has made the first property. The second property, we square it. When you square it, you get 9, and you find that 9 cannot divide 6. So that then means the prime number exists. We found that the prime number exists, and that prime number is 3. And since it exists, by this test, by this Eisenstein's test, we can conclude that this polynomial is irreducible. That means you cannot factorize this polynomial. However much you try, you will not factorize this polynomial. Okay, let's look at another example. Just before that, I've noted something that this criterion, it should be noted that this criterion is sufficient, but it's not necessary for irreducibility. That means it gives us a hint that this polynomial may be irreducible. So if you find that it's irreducible, you may want to carry out other tests just to verify if indeed it's irreducible. That's how I say it means that the polynomial satisfies, if it satisfies this criterion, it's irreducible. Nevertheless, if the criterion is not met, then the polynomial may still be irreducible, and so on. Now, so let me just come back to this example to emphasize to what I've just said. What I've said is, you see, for this case, for this example, we found that the prime number exists, and that prime number is 3, exists. So if it exists, you can say that the polynomial is irreducible. But if the prime number does not exist, you've thought about all the prime numbers and you've not found any that meets those conditions, what we then say is that the polynomial is reducible. It can be factorized. But what I've said is, when you find that the condition is not met, it's not always true that that polynomial can be factorized. It's not always true. Okay, sorry for that. So let's continue. So how do you proceed? Yes, I mean, just a minute. Okay, so let's continue. So what I was explaining was that we're still looking at this Eisenstein's criterion, and there are two possibilities: that we can find a prime number, and we may also not find that prime number. Now, if the prime number exists, we've said that by this criterion, then the polynomial is irreducible. You cannot factorize it. If the prime number does not exist, then it means the polynomial is reducible. We can factorize it. But of course, I also said that that is not always true. It's not always true that if the prime number does not exist, then that polynomial will be reducible. In some cases, the polynomial will not be reducible. So you only need, if you find that the P does not exist, then for you to be certain, you try other tests. You try other tests again. And there's one test that will show you that you can try to verify. Now let's look at this example. Okay, the example says, want to test if this polynomial here is irreducible. So in other words, you want to find if there is a prime number that can divide this number, and fail to divide this number. Then its square can also divide this number. So if you think of that, then is there a prime number P that can divide -9, then divide 3, and fail to divide this? 3 can do that. 3 can divide this, can fail to divide this. Is that okay? But now the other condition is that its square should not divide the constant term. So the square of 3 is 9, and 9 divides -9. So that means 3 is not the prime number you're looking for. Is that okay? It's not the prime number that meets those conditions. Now, what other prime number? 2. 2 cannot divide 9, cannot divide 3, so 2 is not the prime number you're looking for. We then think of 5. 5 cannot divide these numbers. 7 cannot divide these numbers. And those are the only prime numbers less than 9 that we were to consider. So there's no other prime number we're supposed to consider here. So it means the prime number that meets the conditions we set is not there. And so we can say that this polynomial is reducible. It's not irreducible, it's reducible. But of course, I've already said that in this case, where the prime number does not exist, we do not say with a lot of certainty that the polynomial is reducible. We do not say with a lot of certainty. We have to carry out other tests to confirm that. So that's why we said that further methods are needed to check if the polynomial is reducible or irreducible. But by just finding that it does not meet this criterion, that is not a reason enough to say that a polynomial is reducible. Although it gives us some hint, it has given us some hint that this polynomial could be reducible. So this is a hint. So as we even go to other methods, we already have a hint from this criteria. Okay, this is the last example on this criterion. Now, again, we have this polynomial and we want to check whether it's irreducible. So we're thinking of prime numbers, a prime number that can divide this constant term, divide this, and fail to divide the leading term. So I can see 2. 2 is that prime number. 2 can divide 14, can divide 6, can divide 4, and cannot divide 3. So it meets that condition. What about 2 square? 2 square is 4, and it does not divide this constant term. So that means 2 is a prime number that meets all the conditions for this criterion, Eisenstein's criterion. So that therefore means this polynomial, you cannot factorize it. It's irreducible. This polynomial is irreducible. You cannot factorize it. You don't need to waste a lot of time trying using rational roots as we did. You see, we were using rational roots last time. And as we were using rational roots, we had not checked whether the polynomials are reducible or not. But this one can now give you a hint. Before you begin when using the rational roots, because rational roots, you are using them to factorize them. So instead of struggling, first of all, ascertain whether this polynomial is reducible. Then you begin.
What have you said about the roots? If a polynomial is irreducible, it does not have roots.
Yeah, if it's irreducible, has no roots.
Oh.
So what I've then said is that before you check whether it has roots or not, and you are checking whether it has roots or not because you want to factorize it. Before you check whether it has roots or not, it's good to first of all check whether it can be reduced or not. And so to check whether it can be reduced or not, you can check by this Eisenstein's criterion. So Eisenstein's criterion will then tell you this one is irreducible or this one is reducible. And then from there, you can go with the certainty to look for the roots and then factorize it. Because you saw the process of checking for those roots was not short, because you first of all come up with the possible roots, and then you check each of them if f of x gives you 0, and you are checking each one of them, and there are several, maybe the one that it becomes a root will be at the far end. So before you begin that, it's easier. You first of all verify whether what you are checking will be found. Now, so we've said this criterion is very simple, and of course you've seen the steps. It's just 2 steps. One step is you are just thinking of, is there a prime number that can divide and then what does the its square divide the constant term, and then you are done with that. Now, where you find that that prime number does not exist, we've said, then you may want to come up with another test. And so the other test is what we want to look at in the next 10 minutes, and then we are done. So this other test is using reduction modulo P. Using reduction mod P. What is this other? This is this other test. Now, what this one means is this: you're given a polynomial, and once
Umekatika kiasi kusikia. Dr. Sakwa.
okay, you can now hear me. Is that okay? Can you now hear me?
We don't hear you.
We can hear you.
We can't hear
Yes.
you. We can't hear you.
Kimani, can you hear me?
Hello.
Hello.
Yes.
We can't hear you properly.
I think it's a problem on your side because I can hear him clearly.
Okay.
Okay.
I
So
said
let's continue. Now, so we're looking at reduction mode P, and what we're saying is you have a polynomial, you think of a prime number, and then this prime number, reduce this, use it to reduce the polynomial mode P. Just the same we've been doing when you're doing it reduction mode P. You reduce this polynomial. And then the reduced polynomial, check if it can be factorized. Check if that reduced polynomial can be factorized. If it can be factorized, then it means the original polynomial can also be factorized. So I've said using this is another way to check irreducibility of a polynomial by considering its behavior over finite fields. And finite fields, we're talking of Z mod N or mod P, that's what we mean. So this method involves reducing the polynomial. You reduce the coefficients of the polynomial, mod P, and then check whether the reduced polynomial is irreducible or if it's reducible. Now, so I've highlighted here the process of doing that. Step one, you choose a prime number, just as we've said. And then after that, reduce the polynomial, the coefficients of that polynomial. After reducing those coefficients, check whether it's irreducible. Now, if this, I've said irreducibility in this does not necessarily mean, it does not necessarily imply irreducibility in this. However, it provides a hint. So if you find that it's irreducible, then it means the original one will also be irreducible. Provides that hint that it's possible it's reducible. But if you find it's reducible, then it becomes reducible than the original one. Now, if you find that it's reducible, it's good to also try another prime number. This one, you just choosing any prime number. You choose any prime number and reduce the polynomial. This prime number should not, there are no conditions that it must fulfill, like we saw in the Eisenstein's criterion. For this one, there's no condition, so long as it's. Let's look at this example very fast. I'm given this polynomial. Using reducing mod P, check whether this polynomial is irreducible. So I have this polynomial. So I just pick one prime number, I've picked 2. I want to begin by reducing this polynomial mod 2. So this one becomes, of course, when you reduce, you only writing the remainder. When you are doing it mod, when you are reducing mod P, you're writing the remainder. So of course this, that will be 0, is that okay? Mod 2. Mod 2, this will be 0, so 0x cubed. And then this will be 1, x squared, and of course this will also be 1, and this will be 0. So if you do away the zeros, you're left with x squared minus x. So this is our new polynomial, which we can see that it can be factorized, that x is common. You can see that x is common for this polynomial, and you can factorize it this way. Yeah, because what was that? It was, this was the polynomial. So when you reduce it mod P, of course, okay, I just said negative x squared. Of course, this can also be positive. You can add 2 there, because this is negative 1. So when you add 2, you get x squared. And then this, add 2 until you get a positive number. It will be x, but this other one is 0. This other one is 0. So you can see that this can be factorized, that you can write it as that. So that means the new polynomial that we obtained is reducible. When you find that you can find that one that is reducible, you cannot at that point just conclude that the original one is also reducible. You need to again try another prime number and see whether it agrees. If more than 2 agree, then you can now conclude that the original one was also reducible. So I've now decided to use another prime number 3. Reduce this mod 3 with 0. Is that okay? Reduce this mod 3. Add 3 6 times. You get 18. So the remainder is 1. And then this one add 3 2 times. And you have x, you have an x there. So it has again given us a polynomial that can be factorized. So you arrive at this, and this can also be factorized as x into x plus 1. So two prime numbers have given us the same result, has told us that, has given us a new polynomial that can be factorized. So since they have given us the same indication, we can say that the original polynomial could also is also reducible. The original polynomial is also reducible. Also, yes. No, it's 1. So you're asking yourself, for instance, if 3 were to go into, it was negative 17, is that okay? Yes, it's negative, not 17. It was negative 17. So to go there negative 6 times. Negative 6 times this would be negative 18. When you subtract, you get the remainder is 1. For the other way is you take this negative 17 and add 3 times until you get a positive number. And you discover that you add there 6 times. 1, 2, 3, 4, 5, and then 6. You add 6 times, and when you do that, get 1. So it's negative 17. Now, so two prime numbers have told us that they've given us a new polynomial which were reducible, and therefore we can say that this other one is also reducible. Okay, let's just look at this one very fast and then we stop. Check whether this is reducible or not using reduction mode P. So we choose 2 prime numbers, and we just want to see whether we're getting a prime number, a polynomial that can be reduced. Is that okay? Yes. So I begin to choose 3. I decide to choose 3. When you reduce mode 3, this would be, the remainder here will be 1, so x cubed. And then here you're adding 3 how many times? You're adding, if you add it 2 times, 3 times, you get negative 1. So this is 2. Is it? If 3 were to go into negative 10, the remainder will be 2. Is that okay? Yes. And then this one, the remainder again is 2. And this one is 0. So this is the polynomial we now have. And you can see this polynomial can be factorized. For instance, from a distance, you can see that x is common. You can see that x is common, and so I factorize it that way. So using 3, we've seen that the new polynomial we come up with can be factorized. Let's try another polynomial, another prime number, now this time 2. Go back to where the equation is. Now reduce this mode 2. Reduce this mode 2. And this will give us 0, this will give us 0, this will give us x, and this will give us 0. So when you reduce mode 2, you get x. These are a linear equation. So since it's linear, it can be factorized. It's linear. So since it's linear, that one you can factorize that. So what that means, again, these 2 prime numbers have given us reduced polynomials which are factorizable. And so we can say that the original polynomial could also be factorizable. Is that okay? Yes. So I think I need to stop there. But then there's this other example, you look at it. This example, I did not use the method above. I just said check irreducibility of this polynomial. And then I wanted to use the rational root test, which we had learned earlier. So I use it. Then when you use the rational root test, what did I find? I did not find a root. I did not find a root that. So according to the rational root test, since I don't find a root to that, you see, and what is the degree? What's the degree of this? What's the degree of this? The degree here is 3. The degree there is 3. So I've said that since no roots exist, f of x has no rational roots. So the rational root test does not provide any factorization over this. So it does not give us we cannot, if you're using the rational root test, we cannot now tell whether that one is reducible or not. So that means I have again applied another method. So I decided to apply the Eisenstein's criterion to see whether it agrees with the rational root test, because the rational root test has found that there's no root. So if there's no root, there's a likelihood that the polynomial cannot be reduced. Is that okay? So then I bring in the Eisenstein's criterion to verify. If it agrees with that, then we can say that that polynomial is irreducible. Okay, let's stop there. So I think we can stop there.